out of that.
That should be good.
It's okay.
Press OK. Press OK. Press OK. There.
All right, good afternoon, everybody. This is too loud. My name is Tejas Shastry, and along with Elena Bekirova and under Professor Robert C. Haddon, for the last 10 weeks I've been working on functionalized single-wall carbon nanotubes as HCl gas sensors. Now, this whole day is dedicated to presenting primitive nanotechnology, and a lot of it's really practical, field effect transistors, nanowires, and things we see in future devices. But to a lot of people, they might not see a big deal about carbon nanosensors. Sure, but it has an application. But the average consumer might maybe have a smaller scale protecting at home. But the great thing about nanotechnology is that you not only get smaller applications, but also a wider range. Right now, there's a team working on implanting these sensors in the human body and in asthma patients and detecting certain compounds that are present right before an asthma attack comes on. This can be crucial to preventing and detecting asthma attacks. Another big application to these carbon nanotube sensors is air pollution. Obviously, the technology to measure air pollution has been around for ages, but with the technology we have now, we can actually see air pollution as it moves through the city, and it gives a whole new outlook to pollution control. Now, the research I've done for the last 10 weeks has been mainly focused on detecting acidic gases. And the way this basically works is that we utilize the semiconductor properties of the single-wall carbon nanotubes. Pristine nanotubes have a pretty nuclear valence bond with really no holes, minus some from industry oxidation. But when you add a functional group to these nanotubes, it's able to interact more readily with acidic compounds. HCl is the acidic gas that we used for testing during my research. And essentially, we all know that acidic gases donate protons, and the functional groups attached to these nanotubes are able to draw those protons in, creating holes in the valence band, and thus turning these nanotubes into p-type semiconductors. Now, since we have a semiconductor, we can obviously measure the change in resistance depending on the concentration of the gas. And by correlating this change, we get a highly sensitive, low-power sensor. So here are the 4 functionalized nanotubes I used. For a control, I used pure nanotubes with no functional groups attached. They have very weak interactions with the acidic gas. I used also amide functionalized nanotubes and octadecimal amine functionalized nanotubes. The main difference between these is just the longer chain in the ODA nanotubes. They protonate in the same place though. And the last group that we used for this research was the functionalized nanotubes with pyridinol. And as you can see here, the two amide nanotubes both protonate on the oxygen, and the pyridinol, being a more basic compound, protonates on the nitrogen. And this is the actual mechanism that allows the nanotubes to draw the electrons and create resistance. So, the way we prepare these films, basically what we do is we take these nanotubes, we disperse them in a solution, and then we spray them onto a substrate. So obviously first we have to disperse the nanotubes in the solvent and sonicate them. Now the solvent mainly depends on the temperature of the nanotubes. We use DMF, THF, which are common organic solvents. For the pyridinol, we were able to just use distilled water and base. After that, we take a gold glass substrate with these gold electrodes on it, and we spray the solution onto the substrate until the resistance is about 30 kiloohms. Now, these little squares right here are actually interdigitated electrodes, and what happens is that when you spray the nanotubes on, the interdigitated electrodes, the nanotubes form bridges across the electrodes, creating a circuit that we can then measure the resistance of. So obviously you can see 5 sensors on the substrate. We only use 1 of the sensors on each substrate. And here are just the specifications of those. We tried to keep them all under 10 nanometers, but the ODA, we could not actually get the resistance down that low, and it was a very thick film, which normally thicker films mean more nanotubes bridging the electrodes, and thus less resistance. But we'll see why the ODA conductivity comes into play later on. So how we test these films? Obviously, there are circuits where we run electrical voltage through them, and then measure the change in resistance when we expose them to acidic gas. So each film we tested at 20 volts. We wanted to use a lower voltage first, but we'll explain why later. First, we flushed them with nitrogen, and this kind of standardizes the resistance. And as you know, like the acidic gases create holes in the valence bond, and this kind of recovers that so that we can get an accurate reading at each concentration. So after that, we expose these nanotubes to concentrations of 30, 60, or 90 ppm. And each one will go through 4 exposures to the gas with nitrogen flushing between in order to recover the resistance. And we also made sure to alternate the film test. So we did criminal film one day and maybe P2 the next in order to get a substantial recovery time and get more accurate results. So here you can see an overview of the functionalized nanotubes against the pure nanotubes. And I've recorded the change in resistance for just 90 ppm, which theoretically should be the highest change. And as you can see, all 3 of the functionalized nanotubes did much better than the pure nanotubes. And if we compare the P2 and the pyridinol, which were the both ends of the spectrum, you can see it's scaled up. P2, little to no resistance because it's not drawing that protons from the acidic gas. However, with pyridinol, we get a very nice response. There's a clear difference between concentrations. And here you can see how we first expose it to HCl, expose it to nitrogen so that it can recover. And while the P2 doesn't recover as well, the pyridinol seems to recover most of its resistance back.